Hi, my name is Nathanael Cox, and I'm going to talk about harmonic persistent homology. This is joint work that was done with Saugata Basu. So kind of an outline of the talk, we're going to go over some preliminaries. We're going to talk about persistent homology and the barcodes associated with that, harmonic persistent homology and those barcodes, and then finally essential simplices of our simple bars will be related to our harmonic persistent homology. So to start, we want to define a finite simplicial complex. So the formal definition is given here, but you can just think of it as appropriate unions of vertices, edges, triangles into higher dimensions. And then a P simplex is whatever the P-dimensional analog of a triangle is. So a zero simplex is the vertex, a one simplex is an edge, etc. And if we have a finite simplicial complex, we will denote the pth chain group on that complex to be the R vector space generated by all of the elements of Kp, which is a set of P simplices. And so CPK is this direct sum here. And in this construction, the tuple of all of your P-dimensional simplices forms a basis of your chain group. We can make the chain group into an Euclidean space by fixing inner product. And our definition of harmonic barcode is going to depend on this inner product, but it doesn't affect any of the theory. And overall in practice, probably the most common choice that makes sense would be this standard inner product, which turns our basis of simplices into an orthonormal basis. We now want to talk about the boundary map, which maps from P-dimensional chain group into the P-1 dimensional chain group. And its definition is given here. Kind of the key property of this boundary map is given below. That is equivalent to the image of the P plus first boundary map being contained in the P kernel, in the kernel of the P boundary map, excuse me. Some notation to go along with this, ZP of K will denote the kernel of the P boundary map, and BP of K will denote the image of the P plus first boundary map. And we'll refer to these as the space of cycles and the space of boundaries respectively. And kind of the important thing we do with these is if you take, because of the property that BP of K is contained in ZP of K, we can take a quotient space, and that quotient space is called the P-dimensional simplicial homology group, HP of K. And in this context, HP of K will be a finite dimensional R vector space. And now transitioning here, we come to our key definition of harmonic homology, which is originally due to Ekman in 1944. For P greater than or equal to 0, the harmonic homology subspace is the intersection of the cycles with the orthogonal complement of the boundary. Now, because orthogonal complement depends on your choice of inner product, this is why the harmonic homology subspaces depend on your choice of inner product. The important thing to note with these spaces, though, is that they are actual subspaces of the chain space, whereas your typical homology is a quotient space. But we can relate these harmonic homology subspaces via this map that sends cosets to the projection and their projection in the orthogonal complement. And this gives an isomorphism between homology and harmonic homology. And if we have subcomplexes K1 contained in K2, restriction of that projection map from the larger space onto the harmonic homology subgroup, the smaller space, gives a linear map, which we call IP, which makes this diagram commute, where this top IP is the map induced by inclusion on homology of K1 to K2. And now with this construction, kind of a reasonable question to ask is if K1 and K2 are as simplicial complexes are close to one another, then we would want their homology spaces, homology groups to also be close together. And this harmonic homology concept allows us to make this intuitive statement a little bit more rigorous. So for any p greater than or equal to 0, HP of K1 and HP of K2 will be subspaces of the chain space, and therefore they'll correspond to points, these points in these Grassmannians, where BP of Ki is the dimension of the harmonic homology subspace of Ki, and GR dV is called the Grassmannian, and it's the space of all d-dimensional subspaces of a given vector space V. And so the D in this case is our BP of Ki, and the vector space V is CP of K. And if we take the disjoint union over all D, we can get this new space, which we'll call GR of V. And following Lim and Yi in their 2016 paper, we can define a metric on the Grassmannian of V. And in particular, A and for the two subspaces A and B, which we're finding the distance between, they do not have to have the same dimension. So if K is the dimension of A and L is the dimension of B, K does not have to equal L. And then we get this as our metric, where theta I is the ith principal angle between A and B. And now that we have this concept of a metric, we can talk about our stability rigorously. So if K is a finite simplicial complex and K1 and K2 are both subcomplexes of K, for each P greater than or equal to 0, we have this stability. So here's the distance on the Grassmannian on CP of K between the harmonic homology subspaces of K1 and K2. And we can show that that is bounded above by pi over 2 times the square root of this quantity delta P of K1 and K2. And again, delta P of K1 and K2, as you can see here, is the maximum of these sums of cardinalities on the differences between the number of p-dimensional simplices in and p plus 1 dimensional simplices of K1 and K2. Now from here, we can talk about filtrations and get into persistent homology. So if T is an ordered set, we call F a filtration if F is a tuple of subcomplexes of a finite simplicial complex, such that if S is less than or equal to T in your ordered set, that implies that KS is a subset of KT. And then this, because all of these spaces are inclusions of one another, as we are increasing in the ordered set T, we can induce by inclusion a map on homology IP from ST on their homology spaces, and we define the persistent homology group to be the image of this map I sub P of ST. And what persistent homology measures is kind of an idea of how long a homology class persists through the filtration. And we capture this persistence in terms of birth and death times. And if we say a homology class gamma is born at time S, if it's not in any persistent homology class going into S for any S prime less than S, and if a homology class is born at time S, we say that it dies at time T. If this second more complicated expression holds. And one thing that we want to note is that the homology classes that are born at time S and never die, and those that are born at time S and die at time T, are not actually subspaces of HP of KS. And so what we can do to get around that is we can define some other subspaces and look at the quotients of those subspaces and kind of get a space that captures this information. So we have two subspaces of our homology groups on KS, MPST and NPST, and their formal definitions are here, but basically what they tell you, MPST tells you all of the homology classes that are born before time s or that are born at time s and die at t or earlier. And then NPST consists of the homology classes which are born before time s or those that are born at time s and die strictly earlier than time t. And if we take their quotients, then these quotients are going to be in bijection. The first quotient with equivalence classes of homology classes that are born at time s and which die at time t, or those that are born at time s and never die in the case of the second quotient. And once we have this, so the dimension of this P sub P of ST, which we'll denote by mu, here is the persistent multiplicity of p-dimensional cycles. And this second set, B sub P of F, which captures the birth time, the death time, and the multiplicity of the cycles. And again, we only record it for birth and death times that have positive multiplicity. And this set is the set of, is called the p-dimensional barcode associated to F. And an element of that set we will call a bar with multiplicity mu p. And if mu p happens to equal 1, we call B a simple bar. And now we can do a similar construction because of the fact that this diagram commutes for any ks and kt. And the image here of this IPST, we will define to be the harmonic persistent homology subspace. And again, kind of the upshot of the working with these harmonic subspaces is that they are subspaces of the chain space. And so we don't have to worry about quotients here. And as you can see, we define the M and N subspaces exactly the same, just with their harmonic counterparts, whereas the P subspaces, which were quotients before, are now merely intersections with an orthogonal complement. And so again, these PPSTs are actual vector subspaces of our chain space. And then the harmonic barcode captures similar information to the regular barcode, birth time, death time, but this time, instead of capturing just the dimension, we actually record the whole subspace so that the harmonic barcode is going to be contained in the indexing set with the disjoint union of Grassmannians, as opposed to just the positive integers. Now, we can, if we have a nice function, we can generate a filtration from it. So our function is from k into the real numbers is admissible if it satisfies that for any two simplices such that sigma is a face of tau, then f of sigma is less than f of tau. And if you have an admissible function, you can generate actual subcomplexes of k, denoted k f less than or equal to t, which is the inverse image from negative infinity up to t. And this will be filtration. And we call this filtration the filtration induced by f, and we'll denote it by f sub little f. Right. And we now can define the idea of a harmonic filtration function. If you have an admissible function f, this function HPKF that sends an element of the real numbers to the harmonic homology subspace of kf less than or equal to t. Again, this is a harmonic filtration function of dimension p. And now we want to go back and connect stability to our harmonic homology subspaces. And so for any functions f and g from the reals into the Grassmannian on CPK, of which the harmonic functions are, we're going to define the distance between those functions to be this integral here, where inside is the metric on the Grassmannian that we discussed before. And we use this following norm on our simplicial admissible function. And using those definitions, we get this following stability theorem. So the distance between, if you have two admissible functions, f and g, the distance between their harmonic functions when L equals 2 is less than or equal to pi over 2 times, here we have the L equals 1 norm of f minus g to the 1/2. All right, and so now we're going to kind of transition to talking about essential simplices. So in recent work by Basu et al., a simplex is called essential with respect to a given bar if it appears with a non-zero coefficient in every cycle representing the bar. And kind of from applications, such as a simplex plays an essential role, or seems to play an essential role in the birth of a bar, and potentially has some special significance. So we're going to move on to formally defining essential simplices. So if you have a chain in the chain group, the set of simplices that appear with non-zero coefficients in the representation of Z is called the support of Z, and we'll denote it by sup of Z. And furthermore, if we have a bar that is simple in the barcode of F, the representatives of B are denoted by rep of B and are equivalent to these spaces listed below. And this is the set of cycles that represent the bar B. And now the formal definition of an essential simplice, if you have, again, if you have a simple bar, then the intersection of all of the support of all of the chains that are in the representation of B make up the set of essential simplices of B. And if you have a simple bar and a cycle that represents B, the support of Z necessarily contains all the essential simplices, but it could be larger. And so kind of one way to measure the quality of the representing cycle is the relative weights of the essential and non-essential simplices appearing in its support. So to kind of capture that idea, we define relative essential complex content. So if you have a simple bar and a chain that represents that bar, we can denote the content of that chain as this sum over the coefficients of Z that are essential over the sum over all of the coefficients of Z. And this is what we call the relative essential content of your chain. And kind of connecting this back to the harmonics, if you have a simple bar, any non-zero cycle in this subspace, we will call a harmonic representative of B, which leads us to the following theorem that harmonic representatives maximize the relative essential content. So if you have a simple bar and two representatives of B, and one of them is the harmonic representative, then the essential content of the harmonic representative is going to be greater than or equal to the essential content of any other representative. So I want to thank the organizers for putting on this conference. I want to thank you for your time. And I want to thank the Battelle Center for Mathematical Medicine for supporting me at this conference. Most importantly, Doctors Veronica Wieland and Drs. Jayajit Jas. Thanks again.